But before we go into today's thing, there were some questions which came up after the class yesterday, where there was a question which Asim asked and we were discussing it, but apparently the entire class was not with it. So, I just want to make a comment about that. The point is that if you are looking at a Euclidean continuation, so let us assume you have developed the entire theory and then you are looking at imaginary t and real t, and you know for a fact that the analytic continuation is this is valid. Okay? I mean, it could be that this is the analytic continuation which is valid, that does not matter, but let us assume the counterclockwise rotation is what is the correct thing to do. That would mean that the poles are sitting somewhere here and somewhere here. Okay? That is why I can do this rotation. If there are no poles at all, you will get a 0. So, there has to be a pole somewhere in the complex plane. So, this is allowed. This also tells you that you cannot rotate like this because the poles will hit it. Okay? So, only one of the two choices is fine and this is the correct choice. Now, what this has an interesting implication to time reversal. The definition which we have for Euclidean time is I times t. Okay? Now, this is okay, this is fine. I will just write it as t so that you can identify these two. This is just t. So, what is happening here is that when you have this definition, and if you look at the normal quantum mechanics, time reversal is t going to minus t, and it is always accompanied by I going to minus I in normal quantum mechanics, and then everything will be the same, like e to the minus I e t will become e to the minus I e t, and Schrodinger equation will remain invariant, etc., etc. So, this is the standard prescription in ordinary quantum mechanics. But if you take this combination and you put t going to minus t and I going to minus t, it will not change. So, in other words, this object Te just goes to Te under time reversal invariance. This in turn means that you cannot do Euclidean theory and convert Te to minus Te, which is obvious, because if you take the expression for the action which we wrote down in the Euclidean theory, that when like integral there are constants dTe or I times action went into this quantity, then half m x dot square in the Euclidean plus v. So, this was all positive definite. Now, if you change Te to minus Te, nothing will happen inside this because it is a square, but this will flip the wrong sign, and the whole idea of getting this negative exponential will be lost, which is equivalent to what does T going to minus T mean? That means you are taking Te to be minus It, but we have just argued that this rotation is not allowed because it is hitting the poles. So, the whole thing is internally very consistent and you can do it like this. The question yesterday which we were discussing is the distinction between time reversal invariance and causality. Time reversal invariance exists even in normal quantum mechanics, but normal non-relativistic quantum mechanics has no, okay, everything has a causal notion, but it does not have the notion of relativistic causality based on light cones. But when you do field theory, you have a relativistic notion of causality based on light cones in the Lorentzian frame. But the Euclidean propagator in the Euclidean plane knows nothing about light cone, at least so we thought. But then when you do everything consistently, the light cone structure comes up. The reason I mentioned it is that we are going to come back to it when we take up Rendler frame, and some of these questions here is, believe it or not, is as recent as 2 months old when we have tackled it, because it is not very well understood and we have to do some work to keep it all perfectly fine. So, we will talk about it. It really happens only when you do this in Rendler frame. In the Minkowski frame, everything is fine, and this is the answer to that. Okay. Now, let me proceed further. Yesterday we stopped here. So, I said that the 4-dimensional Fourier transform of this is given by this object, and you can write it in this form, and I also derived this form, both of which we will be using today. So, just commit them to memory. Now, let us go and ask what is the 3-dimensional Fourier transform is. Okay, so the textbooks, all the textbooks in field theory will give you this. Okay, while the 3-dimensional Fourier transform is actually somewhat more interesting, but it is not given in many textbooks. What you are doing here is to take x1, x2, which you will have t2 minus t1 and capital X2, I mean boldface x2 minus boldface x1, which I call x, and I am just going to do a Fourier transform on just the spatial variable. So, you again go back and write down the integral representation for the Green's function, which is d mu over mu square e to the minus m square mu. I have sort of omitted mentioning I epsilon. You imagine that there is an I epsilon. Then you take the time part out and just keep the spatial part in, and then you do a Fourier transform. It is straightforward. You do that. When you do this, what you are going to get is that this integral on this side is going to be of the form, there is a t square upon some quantity, that mu I am going to call as rho square. Then here, when you do a Fourier transform, this is going to be another Gaussian, this is going to be a Gaussian, and that Gaussian is going to combine with this. So, there is an m square here and a p square here, and hereafter wherever you see a symbol omega p square or omega k square or whatever, it stands for p square plus m square. This is the relativistic energy of a particle with momentum p. Okay. So, that will nicely combine to give you this, and then you have an integration with a Gaussian and an 1 by r square. This can be done, or you look it up, and this integral with a and b here has this form. The important thing here is that the left hand side is an even function of a and b, which means the right hand side has to be an even function of a and b. So, what you get here is not a b, but modulus of a and modulus of b, which when you work it out, you will find that it is actually true. So, you go and plug it in here, and you find that one of them is omega p squares. So, it is modulus of omega p square, which is omega p, but omega p is defined with a positive square root all the time. Okay. Then you have a t that is going to be defined with a modulus of t. So, the final result is that this Fourier transform is enormously simple. It is just exponential minus I omega p with a modulus of t divided by 1 by 2 omega. Compare this with the non-relativistic, okay, so that I have not written it here, but we will come back to it. If you remember, or I think it is there in the next slide, let me just see. Yeah. So, this is the relativistic expression 1 by omega p e to the minus I omega modulus of t. In the non-relativistic case, we did do that. Remember, we said that it has to be e to the minus t I t times some function of p, and I said that if that function of p is just the energy, you get the correct propagator. But of course, after that we have derived the correct propagator, so you can go and do a Fourier transform, and this is exactly what you will get. So, what is happening here is that in the non-relativistic case, we could sort of say that it is only propagating forward in time, but in the relativistic case, it comes with modulus of t, which means that there is a propagation which is both backwards and forwards in time. Of course, there is propagation backwards and forwards in x as well, and x is just like t, but the time backward propagation is always very important. So, that is why it is being stressed, and what you find is that this entire object, that is, this is the Fourier transform. So, you Fourier transform it back. So, it is d3 e to the I p dot x, and you plug in this quantity. That has the form, here it is theta of t e to the minus I omega t and e to the I p dot x, that I am going to write as e to the I p x. Again notation. So, normally when I write p x, it is a 4 vector. So, it is p0 times time and p dot x, and this p0 is taken to be this omega p. Okay. So, the p dot, because we are using the signature for this lecture to be plus minus minus minus, this comes with the positive sign. So, as a result of which, when t is positive, this is e to the minus I omega t, and then you have a p dot x. So, this is e to the minus I p x. So, get used to the notation that p x stands for a dot product in 4-dimensional space, but the p naught of that is not an independent variable, but it is actually the omega p. I stress this because this is different from what occurs, for example, here. In this integral, I put a dot in the middle, and hopefully I will be consistent everywhere. If I put p dot x, what it means is that this p naught and this p are independent variable, and we are actually integrating over all the 4 of them. But when I do not put a dot and I write p x, do not believe me too much, I might end up being inconsistent once in a while. The context will define what it is. When I do that, its zeroth component of this object is defined in terms of the vector by this relation. It is, the technical term is, it is on shell, okay, while the other one is off shell and all the 4 are independent. So, this is what you get for t greater than 0, and when t is less than 0, this just picks up a minus sign. You might wonder, I mean, because if I take t is negative, then modulus of t is minus t. So, this of course will pick up a e to the I plus I omega pt, that is fine, but this seems to be p dot x. So, you should get both with plus sign. There you play a slight trick. You, in the second term, you change p to minus p in the integration just to get everything nice. So, that p changes and omega p is mercifully independent of sine of p, it only depends on p square. So, you can write it like that. Finally, I have to define for you this symbol. This symbol essentially stands for whatever is remaining, it is d3p, 2 pi the whole cubed and 2 omega p. So, let me write it down because this is going to appear every once in a while. D omega p is defined to be d3p upon 2 omega p, where omega p is square root of p square plus m square, and then 1 over 2 pi the whole cubed is added for taste. It really does not matter. This combination is important. That this combination is important, you can already guess from here. The left hand side is a Lorentz invariant biscalar or a scalar. E to the minus ipx is Lorentz invariant. We will come to theta function in a minute. Then this has to be Lorentz invariant, and the way to see is that this particular object is actually Lorentz invariant. How do I know that? You should work it out, but I will indicate to you what happens. If you take the integral d4p and then you put a Dirac delta function on p square minus m square, p is 4-dimensional vector, and then you put a theta of p naught, so that you only take the positive root in this. This quantity is Lorentz invariant. Then you use the rule for how to convert a Dirac delta function of a function, and that will give you its derivative evaluated on the Dirac delta function in the denominator. That will give you this 2 omega p. So, this object, in spite of its appearances, is a Lorentz invariant quantity. So, this is the correct measure to use in the integration. Of course, you can use just d3p, then the other quantity has to be defined with a root 2 omega, and its transformation properties will be different. For convenience, we might use d3p or this, but here I have written it down like this. Now, at this stage, of course, you should start worrying. There is a theta of t, which means, remember, t is t2 minus t1. So, either t2 is greater than t1 or t2 is less than t1. Is that Lorentz invariant? Now, the time ordering between two events is Lorentz invariant if the two events are time-like separated. If 2 points are time-like separated, and if I say one is to the future of the other, that is a Lorentz invariant statement. It stays true in all Lorentz frames. But if 2 points are space-like separated, this is true for every x2 and every x1 on the planet. So, if there are 2 points which are space-like separated, then whether something is greater than t2 is greater than t1 or t2 is less than t1 depends on the frame of the observer. Therefore, for consistency, it should happen that this particular integral with this d omega p and this is actually equal to this d omega p integral with this when the two events are space-like, but they should be different when the two events are time-like. And quantum field theory is consistent. If you check it out, you will find that this strange thing actually happened because of very nice gimmicks which will go on. Again, you will find it in my book. It is well known. I mean, it is there in several books, and but it is a good point to remember. So, the whole thing is Lorentz invariant, even though there is propagation forward in time and propagation backward in time. Fine. Now, let us proceed a bit further. So, this I had already told you. They look remarkably simple, but yet the features are completely different. What is more, at this stage, if you have a very, very good eye, you will see a harmonic oscillator. You may not, but yesterday we derived it. I said that if you have a harmonic oscillator with d square by dt square plus omega square, and I write down the Green's function and I go to the Fourier space, right? You get a Fourier transform of a Lorentzian, and that is e to the minus I omega modulus of t. And if you do everything correctly, the constant factor will be 1 over 2 omega p. So there is something funny going on here. We started with a relativistic particle and its action, which is square root of 1 minus v square by c square into dt, and we evaluated the propagator by summing over all paths. So we just took one particle going from here to here, and then we did all the sum over that, and finally we find the propagator. The propagator is a Macdonald function, it does not tell you anything, but if you take that propagator and Fourier transform with respect to say with respect to just the spatial coordinates, lo and behold, something like a harmonic oscillator appears. We will see more hints of this as we go along. So before we get into formal theory, I want to show you a fun thing. This is not very rigorous. I will again tell you where the lack of rigor comes in, because we will be manipulating divergent quantities. It can be made more rigorous by using something called dimensional regularization, which I am not going to go into. So we will manipulate divergent quantities, but the result is quite interesting. Suppose you have this g of x2 minus x1 or whatever we wrote down here, this quantity. Now this is in 4-dimensional space, and what is really distinguishing the relativistic propagator from a non-relativistic property? That is the existence of closed loops. So what I mean by that? Let us take t and let us take x. And if you take one event here and one event here and a particle is propagating, then I know if it is just propagating, not hitting the t-axis more than once anywhere, then it is almost like a non-relativistic particle. And you can of course have paths like this, which we talked about, said that it is cutting it at 3 different places, and if it can cut at infinite number of times, and then you need infinite degrees of freedom, etc. But there is also another interesting thing it can do. This is t, this is x, and you can have a path like this. There were no particles here, there were no particles here, but in between a particle just went around in a loop. So there is a closed loop. So x1 is equal to x2 in the propagator is what we are saying. What is the amplitude for a particle to start at a point x and come back to that point x? Okay. Now this cannot happen in non-relativistic quantum mechanics. Of course, in non-relativistic quantum mechanics, a particle can start at some spatial location and come back to that spatial location, but it can't come back in time. To come back in time, you need to have propagation backward in time, and that is what we have achieved. There is something interesting you can do with it, which I wanted to show you. So you take this amplitude, which is for the particle to start at 0, in a time mu, it goes from x to x. So this is that amplitude. But suppose I want to ask what is the amplitude that it does this, carrying an energy E with it. So the usual quantum mechanics tells you that you have to just put in a phase factor e to the I e mu and integrate over d mu. So if you do that, you get, I am just defining it as the probability that the particle is going to travel in a loop containing a point x with an energy E. Now I want to say that, look, I don't care what is the energy, so I am going to integrate over all energies. So I have 0 to infinity integral of dE of this quantity, and I throw in a half because the loop can be transverse either in this direction or in this direction, and I just want to take one of them. So there are both these loops are contributing when I say x2 is equal to x1. So this is some E defined, and it only depends on the location x. The reason I defined it like this is that this amplitude which I have defined right now is for a free particle. But in principle, you can do this for a charged particle in an electromagnetic field or a charged particle in a magnetic field. In that case, you will find that there are non-trivial expressions for this EFX which you will get. This is roughly speaking the energy of the vacuum fluctuation, because in the vacuum there is a loop which has taken place. It is just a virtual particle, or you can think of a particle-antiparticle pair being created and annihilated or something. We haven't done any of that yet, but you can think in that line because you know what is going to come. So this is like the energy of that, which of course you can work out. You do the integral and you get minus 1 by I mu. You assume that e to the I infinity is almost always 0 in the sense that it can be regularized away. So only one of them contribute and you get this. This quantity I showed you a little while ago, that it is e to the minus I mu box with between x and x. and there is an extra mu sitting here. So, this is the energy which we are trying to compute. You can relate it to the Green's function. So, how can you relate it to the Green's function? I am going to take this E and differentiate it with respect to m square, Green's function or the propagator. So, if you differentiate this with respect to m square, I am just going to pick up a minus I, that will take care of this, and this since I am differentiating with respect to m square, this mu will come down and cancel it out. No, I do not even know what this energy is. It is the energy with which the particle is propagating. If it feels like it may carry rest energy, otherwise it may not. We will see what it is. Okay. So, so far it is just a formal definition of the vacuum fluctuations. Yeah, that is right. Okay. So, you get the relation that the derivative of that Greek E or calligraphic E with respect to m square is just the coincidence limit of the propagator. Okay, what is this? Now, the coincidence limit of the propagator, you have to put the spatial coordinates equal to 0, x is equal to 0, and the time difference to be 0. We already know that in the Fourier space, the propagator is 1 upon 2 omega p e to the minus I omega modulus of t. That modulus of t goes to 0, so you get 1 upon omega p, and the spatial coordinates goes to 0. So, when you do the Fourier transform, you are only going to do this d3p integration. Now, this quantity happens to be infinity. So is the G, or rather the coincidence limit of this is infinity. That is quite easy to see right from this thing itself. So, in this, if I put x1 equals x2, this x will go to 0. So, you are integrating d4p, and the maximum power of p which is in the denominator is p square. So, it is a p square, p cube dp divided by p square, that is divergent. But that is all right, we will not be afraid of divergent quantities. So, you work this out, but what is interesting is that it can be written in a different way. Yeah. No, no, it does not depend on the path, because I have gone and come back to the same point, and you find that all the information about the path is gone.
So, irrespective of the...
Exactly, exactly. Okay. So, this is the integral, but what is really remarkable is that this can be written in an equivalent form. Suppose I take d3p upon 2 pi the whole cube, which is just staying here, and then I take half h cross omega p. Okay. Now, if you differentiate omega p with respect to m square, so omega p will be square root of this quantity. So, you get a half, which is good because you need 2 halves, and then it will go to the denominator, and I am differentiating with respect to m square, so it will give me 1. So, this is actually equal to this, and this quantity is equal to this. So, the derivative with respect to m square of this quantity is same as derivative with respect to this of m square. So, if I integrate back, there will be some constant, but I am going to throw away the constant for the moment, and then what I get is this result. Now, this is beautiful. This is beautiful because what we did was to start with a particle, single particle presumably, which went from point to point. We gave its relativistic action from what we know in classical relativistic theory. Then we summed over the paths. If you want, you could have done it very rigorously by doing a lattice and regularizing, etc. So, you got a propagator. We continued back into Lorentzian spacetime. Then we said, hey, lo and behold, now I can have closed loops. So, I said there are these closed loops. Then I asked, what is the amount of energy these closed loops, which are like vacuum fluctuations, are carrying? It's all relativistic particle going around in a loop. But you find that that energy is the same as sum of the energies of harmonic oscillators, 0 point energies of the harmonic oscillators. You associate one harmonic oscillator with every vector p, and the frequency of the oscillator you set it to omega p, and if all these oscillators are in the ground state, they all will give you half h cross omega p energy, and you just integrate it over d3p, you get this energy. So far we have not, so the summary is that you take this, so this is exactly what I said in word. Everything on the left hand side is based on action for a relativistic particle, no fields, no oscillators, nothing. Particles is going and coming back. Then we suddenly realize that closed loops are allowed. Then we want to look at the energy contributed by the closed loops, and you find that it is an integral over the harmonic oscillator's energy. Of course, this is divergent. So, in that sense, that is why I said it is a bit heuristic, because it is not a rigorous result, but believe me that it can be made rigorous by some technique called dimensional regularization, but this is what you get. So, this is our first hint that what you can describe with your relativistic particles action and path integral can also probably be described by infinite number of harmonic oscillators. But at the very first lecture I told you that if a particle is doing like this and you want a causal behavior from one time to another time to another time, etc., you want some system which has infinite number of degrees of freedom, and if I have infinite number of harmonic oscillators, that is good, and this infinite number of harmonic oscillators will turn out to be a field. Yeah. Well, it is just a word. Right now we only know the energy associated with a closed loop. Yes. In this particular case, everything, this is related to his question, the shape of the loop, path of the loop, all of them go away. Okay? There is no intrinsic time scale associated with it. Of course, there is a dimensionful quantity on the right hand side. You are integrating over p square, but if you put square root of p square plus m square and you decide to integrate it with a cutoff, then that m square will kick in and you will find the final result to depend on m, and that m sets a time scale or a spatial length scale. No, there are two scales. One scale is the cutoff you put. That is, just out of desperation. Okay? The another scale is the scale which comes from theory. That is the mass of the particle. So, there are two scales in the problem. The ratio of this will come up. In fact, in a much later class, assuming I get around to that, I think I will. When we do the cosmological constant problem, lot of people will tell you that the half h cross omegas add up to a cosmological constant, etc. We will spend some time trying to see what it happens in the regulator, etc. Okay? So, that is what happens here. Yeah.
Maybe I'm jumping, but this is true for free particle where all space-time points are similar.
Yeah.
What if there is some external?
Then you will find results which depends on EFX. For example, if it is in an electromagnetic field, you will find, if you take a pure magnetic field, then this energy is what is known as the energy of the vacuum polarization. If you take an electric field, this can be the energy of pairs created out of it as well as the vacuum polarization. Okay? So, it is a very real effect. That original formula I wrote down is absolutely correct in all these cases, and if there is a field which is varying slowly in space, you can calculate how that field energy is varying in space. Again, there won't be dependence on the shape of the particle, because the loops just go out of, and only in the end you get this answer. No, it won't depend on the loop, the shape of the particle. Yeah. Right. Okay, so now that we have seen harmonic oscillator, let us go and revise what we know about harmonic oscillators, and I will try to connect this up with the field theory. That is, we haven't so far seen a field. I mean, I only got a result which is essentially infinity equals infinity, and try to convince you that there are oscillators there, but we will do it more rigorously. Yes? Actually, in a generic process also infinite oscillators will come, but that I have not shown yet. I am going to describe that. Yeah. So, rapid recall on oscillator. So, when you set everything to unity or rescale variables, the Hamiltonian for a harmonic oscillator is half p square plus q square. The non-relativistic Hamiltonians always has a p square, and oscillator is the only one which has this thing also has a q square, which means p going to q is a symmetry, and that is why harmonic oscillators have such beautiful properties, and we spend all our time studying them. Okay, no other system will have this. Then you can write this as q minus ip into q plus ip. If you multiply them out, of course you get the normal things q square and p square, but then you will have a q and a p and a p and a q, they do not commute. Therefore, you have to subtract that quantity out. This quantity I will call a dagger, this quantity I will call a with the square root symbol. So, this whole thing becomes a dagger a, then this quantity becomes half and this is half, and the a dagger a is what is called the number operator, it is n plus half. Okay, and the number of terms has integer eigenvalues, so the Hamiltonian has integer eigenvalues, A dagger and A are creation and annihilation operator, etc., etc. So it is just to remind you how this comes about. Now, if you throw in things which you are set to unity, we don't want mass to the oscillator, so mass of the oscillator will keep it to be unity, but we want the frequency. Then here, of course, if you have A defined by this, or rather A dagger defined by this and A defined by this, if you add them up, you are going to get capital Q. So capital Q is like A plus A dagger, and when you put the scalings correctly, it will turn out that the what you call the dynamical variable Q of the oscillator is just 1 upon root 2 omega into A dagger plus A. Okay. Now, you solve the Heisenberg equations of motion, you will find that this A dagger and A evolves as e to the minus I omega t and e to the omega t, and 1 over root 2 omega goes for a right. This A stands for A dagger at t is equal to 0, and this stands for this at 0. Okay. So this is textbook, and in fact NRQM textbook. So this is what the evolution says. What I am going to do is, just for convenience, instead of one oscillator, I am going to take two oscillators. I'll tell you why. I mean, it is just purely technical point, that normally in when you are talking about harmonic oscillators in quantum mechanics, you want Q to be Hermitian, or classically you are thinking of a real oscillator that becomes a Hermitian operator. While in quantum field theory, we are going to eventually find this Q to be the Fourier transform of a field. So then the reality condition you cannot easily maintain. So you take care of that by thinking of it as a complex oscillator. So it has a real part and imaginary part, and both are oscillated with the same frequency. This is not of any deep significance. So I take two real oscillators and think of them as one complex oscillator. So half x dot square plus y dot square minus half omega square x square plus y square. So that can be written if you, okay. So that can be written as, if you take x plus iy as one variable, this is q dot with a q dot star, or mode q dot square. This is mode q square times omega square. Okay. So this is the oscillator I will be looking at. Now these are oscillators, so I know that x goes as some alpha e to the minus I omega t, alpha dagger e to the I omega t. So alpha and alpha dagger are the creation and annihilation operators for the x oscillator. Similarly, I have a beta and beta dagger for the y oscillator, and of course alpha and alpha daggers has the standard commutation rule. Alpha commutes with alpha, alpha dagger commutes with alpha dagger, alpha dagger commutator is 1. Similarly for beta, and beta and alpha commute with each other. Now you go a bit further, and you, of course, first you obtain your Q, and the Q is defined here as, this Q is x plus iy. So if you take that, you get alpha plus I beta e to the minus I omega t, alpha dagger plus I beta dagger e to the I omega t. So I have a complex oscillator. So for the complex oscillator, you have an A and a B dagger. Okay. I mean, if it is a real oscillator, B would have been A, but because it is a complex oscillator, I am going to keep it as A and B dagger, where these are the identifications I have made and these are the commutation rules. Again, all this is just window dressing. Now what we are going to do is, we had one oscillator, we had two oscillators, 3, 4, infinity. You take infinite number of oscillators. What do? You stick in a symbol P to it. So because we know that eventually, in order to do something, you can think of it as a well motivated way of doing it, or you can think of it as definition. Let us just consider this system, where for every vector P, I am going to associate an oscillator with a degrees of freedom QP, and it has an AP as the annihilation operator, and BP dagger would have been the creation operator. Just for future convenience, I will identify it with minus P, which is again at, it is a question of which oscillator I am identifying it with. So in one case I will identify with P, and the other case I will identify with minus P. It just turns out to be, to flip that P at a later on, it turns out to be very convenient to write a manifestly Lorentz invariant expression. So your Q dagger is going to pick up a dagger here, and this is complex conjugated, and this dagger goes away and this becomes minus. And now you have a continuum of them. So you are going to normalize it. Instead of saying 1, it is a Dirac delta function of P minus K and P minus K for both of them. Yeah. So far we have not said anything about Lorentz invariant. I am just taking infinite number of oscillators and studying them. This could be phonons in a solid. Okay? Lorentz invariance will come, but so far I have not said anything, and in particular I have not said what omega p is. The information about Lorentz invariance is contained in the dispersion relation. If omega square happens to be p square plus m square, this system will be Lorentz invariant. Okay. Now comes the most important part, which is some of you must have done it in your class, but I will just mention it and explain it to you. If you construct from an oscillator the following quantity, this is essentially a complicated way of writing the propagator. You take the QK, the dynamical degree of freedom at time t2, then you take QP dagger at time t1, and then you introduce what is called a time ordering operator. So, the time ordering operator just says that the time ordering operator just says that if T2 is greater than T1, you do nothing, you leave it like that. If T2 is less than T1, you flip them. So, the time ordering of two variables A of T2, B of T1 is A of T2, B of T1, and if T1 is greater than T2, you flip A and B. Okay? That is what we do here. This quantity can be computed. This is just harmonic oscillator physics. So, assume for example T2 is greater than T1, then you have a Q and Q dagger between the ground state of the oscillator. Q dagger will have a and A dagger, and that acts on the vacuum and it will create a non-particle state, and the other one has to annihilate that non-particle state, etc. All that will survive is e to the minus I omega t's, and in one case you will get T2 minus T1, in the other case you will get T1 minus T2 with a minus sign. So, you end up getting this. So, you can see that this 2 pi the whole cubed and delta function comes from these kinds of commutators. Okay. That is not so important, but the rest of it 1 by 2 omega e to the minus I omega t is what we saw long back. Just to remind you what we saw, when did we see this? Yes. Yeah, here. Okay. So, it is the propagator for the harmonic oscillator which can be written as the time ordered product of its dynamical variable, and that is what is giving you this. So, let me get back to this. Yes. So, you have this. What we are going to do, so this has these indices k and p sticking out here, and this has delta k and p here. Now, I can take e to the I times some k dot x and e to the I p times p dot y and Fourier transform it, or rather build it up. So, if you do that, you take this time ordered product, then you stick in a e to the I k x2 for this and p x1 here, and you integrate over p and k. But these are just C numbers, so I mean they are not operating on a vacuum or anything, so I can take it and plug it into this. So, I get a qk of T2 e to the I k x2, and you get a qp dagger e to the minus ipx. These things I define as a field, that is this phi of x is defined to be d3p qp of t e to the ip dot x. Its time dependence comes from t, which we know is e to the minus I omega t because it is a harmonic oscillator. Its spatial dependence comes from e to the ipx, and therefore, once I have plugged it into this, I can write this whole thing as a time ordered product of this phi and phi dagger. So, let us pause for a minute and see what we have done. We had originally a time ordered product of these oscillators. So, I just plugged in this Fourier transform, and this time ordered product with this e to the I k dot x1 of course is my Green's function. Why is that? Remember what we derived originally. We almost had it here. We had e to the minus I omega modulus of t upon 2 omega k. If I had stuck in a e to the I p dot x and integrated over d3p, I would have got the correct thing back. In order to maintain Lorentz invariance, I have to divide by 1 over root 2 omega, or when two of them are appearing 1 by 2 omega. That does not matter because I can redefine my oscillators, that is the A daggers and A's with that factor. This has only root 2 omega. So, you put another 1 over root 2 omega here and put a root 2 omega here. So, root 2 omega times AP will be a Lorentz invariant creation operator and annihilation operator. But most of the time people like to work with this because they have an intuition coming from oscillators, and oscillators have 1 over root 2 omega. So, this is a Lorentz invariant object with the proper definition of AP and BP dagger. Okay. So, now we have got a phi, and we have shown that the propagator is actually the vacuum, the ground state expectation value of the oscillators which make up this field phi, and out of that you can build this propagator. So, in fact, I have written it down here for those of you who want to see everything in a manifestly Lorentz invariant manner. So, suppose you set square root of 2 omega times AP, you put a square root of 2 omega there and divide by this. So, this becomes d3p upon 2 omega and 2 pi the whole cube, which is what we were looking at here. That is d omega p. Then you get a capital AP e to the IPX. Then you get a capital BP dagger e to the IPX. So, in fact, it is a sum of two fields. This is going to be important. So, let me stress for a minute. So, this phi which I have built is the sum of one field here and another field here. You can take the dagger off and dagger off, then that is BP times e to the IPX. Both are perfectly Lorentz invariant fields. They both have e to the minus IPX kind of behavior, and those of you who know something called Klein-Gordon equation will immediately see that these modes actually satisfy the Klein-Gordon equation, because e to the IPX is going to be the solution to the Klein-Gordon equation. So, I have two fields A and B dagger, sum together gives you this phi. Yeah. That is correct. So, that is the whole trick, because when you stick in this, you have only, I told you about it even before, that is, it has only e to the minus I omega t. One part is fine, e to the minus I omega t plus IPX. In the other part, I have e to the plus I omega t and minus IPX. I do not like that. Nothing will go wrong if you stick it, it will just look cumbersome. But here I can write everything in a nice Lorentz invariant way. Okay, it is just like writing the propagator. Okay. So, you get this and you have two scalar fields, the sum of this is phi. Now, this is a moment where it is sort of another high point in the lecture, in the sense that what I have proven for you is this relation, which I claim nobody understands, and in fact, I have explained in this paper why nobody understands that. Okay. Now, let me, this is serious stuff, in the sense that it is not some trivial not understanding it. What is on the left hand side is a sum over path of a single relativistic particle with the action for a single relativistic particle. And we summed it, let us say, on the lattice. I mean, we did it with a Jacobi action trick, but I could have summed it on the lattice. So, when you do that, I get an expression. So, I know the algebraic form of this, it is a Macdonald function. Then I have shown for you, first of all, that it can be expressed in terms of a field, which is made of two parts and a time ordering of the 2 points in it taken in the ground state. And this ground state is defined to be the ground state of the oscillators to which the field is decomposed. Otherwise, I do not know what a ground state is, I just have a field. Okay, but I know what is a ground state of an oscillator is. So, if you decompose the field into oscillators, then I get a ground state, and then I can take that expectation value here. If I expand this time ordering, what you find is that there is a theta of T2 minus T1 when you put this A and A dagger and all that. There is one field which comes in here, and if the theta is opposite, that is, instead of T1, if T2 is greater than T1, one field kicks in. If T1 is less than T2, another field kicks in. If you work all these things out very properly, and again go back and read my QFT book where I have spent quite a few pages on that, you will find that this corresponds to the particle and this corresponds to the antiparticle, or vice versa, depending on your taste. The actual field is a composition of these two, and this is a remarkable result when you put relativity and quantum mechanics together. To every particle there has to be an antiparticle, and if you have worked with a real scalar field, which most textbooks do, and I think it is somewhat pedagogically incorrect, its particle is same as the antiparticle, so you won't be able to distinguish them. But if you take a complex scalar field, then the particle and antiparticle carry different charges and they are distinct, and this is what comes out. At this stage, a question arises, or at least it should arise. Why do I need phi? Why not just work with A? Okay. A is Lorentz invariant. It is a scalar. It is nicely built out of e to the minus ipx, etc. It has only positive frequencies, but so what? And it looks like a good field to me. And why don't I work with that? And that reason is very, very deep. The reason you cannot work just with A, but with you need A plus A dagger, is that I am not going to prove it to you, but let me explain to you what happened. If you take 2 points in a space-like surface and you want to make a measurement of the field at one point, you do not want it to affect the other one, because space-like surfaces are supposed to be causally disconnected. If you work with just A or B, you will find that they do not commute on space-like points. So, if two objects do not commute, then there is an uncertainty principle which kicks in. But if you take A plus B dagger, this phi commutes on space-like interval. A does not, B dagger does not, but A plus B dagger does. So, there is a very deep reason between this kind of relativistic causality, that if I make a measurement here in a space-like location, it should not affect something else, and the existence of antiparticles. This again, I have a whole section in my book called "Why do we need antiparticles?" where I have described it. So, go and read it up if you want something more, but we do not have time to discuss it. This is also very nicely described in Weinberg's quantum field theory book. That book, if you want to plot through everything, it is a bit difficult, but there is a section in which he has explained why you need the two of them, and it is not explained so well in other textbooks. So, it is a good point to keep. But coming back to this relation, there is absolutely no clue why this is true, in the sense in which I explained to you. Without doing all this calculation, the calculation is, you will admit, is a bit laborious, because in order to compute this rigorously, you need a lattice calculation, or you need to have Jacobi action, etc., etc. It is a square root action, it is not easy to do. You do that. Then you have to look at the Fourier transform with hindsight. You should understand there are harmonic oscillators and develop the field, introduce the time ordering operator and do this. So, after this elaborate calculation, you get an enormously simple result that the relativistic particle gives you quantum fields and vice versa. You can either start with this quantum field, and that quantum field, the excitations of that quantum field can be described as relativistic particles, or you can start with a relativistic particle and obtain that. Almost every one of you would have studied the quantization of a relativistic field. That is why I took the inverse direction. So, there were two hands up. So, you, yeah. If you take phi at a point x and phi at a point y at the same time, okay, or phi dagger in this particular case at the same time. So, it is a constant time hypersurface at two spatial location, they will commute. But if you do the same thing with A or same thing with B, it will not. There is a subtle cancellation between A and B which makes these quantities 0. Did you have an? Yeah. Yes. Yes. Okay. Actually, it is more like what I didn't put in. I didn't say anything about the spin. I actually also didn't say anything about the charge. So, what you should have got is a neutral scalar field. But I actually got a complex scalar field which is charged scalar field, because I am assuming that it has a charge, but there is no electromagnetic field externally. Then the action is the same. Yeah. Yes. This is one reason why we all say that path integrals are elegant, useless things, because these beautiful path integral things work very well for a scalar particle. It also works for a Dirac particle. You have to do a little bit harder work, and because it is harder work, it appears as an exercise in my QFT book, but you can actually get the Dirac propagator out of that. Okay? But if you are taking any higher spin particle, even photon, there is no elegant path integral from which you can write down the photon propagator to go from one point to another. Okay? So, there is very difficult to incorporate spin. There is huge amount of literature on it. I mean, people have tried it, okay. But and you can also, once you know the result, you can cook up something, but nicely and elegantly you cannot get this. But that comes out beautifully when you start with the representations of the Lorentz group, and that is why the approach, the standard approach, canonical quantization approach, has a lot to offer compared to the path integral approach. But I took this path integral approach because I am assuming that you will anyway be bored to death with canonical quantization in some of the courses. So, you would learn it. But this you won't learn, and that is why I took this approach. Yeah. If someone could come up with a, so this is in some sense again an open problem, and I can give you references if someone is interested. If someone can come up with a nice way to incorporate spin, even photon, to get the propagator for the photon to go from one point to another, by using a path integral, so that you get the correct result, that will be beautiful. Okay. But it is an open problem, but this does not belong to the class of open problems which I said are doable problems. This may or may not be doable. Yeah. Oh, that really does not matter, because the massless scalar, the point is normally in non-relativistic, in the classical relativistic theory, you put minus m integral dl. So, if I put m is equal to 0, that will go away. But you do not have to put that m, that is just a constant factor. So, you can discuss null geodesics and things like that, that works out. In fact, that we did in the last lecture, I mentioned it to you, you do rescaling in such a way that the m goes away and it sits as e to the minus I m square. Therefore, I can study 0 mass particles by that same property. Okay, fine. So, as I said, we do not understand this, and this is a good thing to worry about. Yeah. And there is also this issue about if you have a particle and antiparticle here, in a moment when we go into accelerated frames and all that, does all these things carry through? It does, but it is a bit subtle. Yes? Yes. Left hand side will be the same. See, in the left hand side, I have said it is a complex scalar field, but a complex scalar field and a real scalar field are distinguished at the classical action level by whether I am adding a q ai dxi electromagnetic coupling or not. But I had just said that it is a charged particle, but there is no electromagnetic field present, and that is how I am working it out. So, the left hand side will be the same, but in the right hand side there will be this difference, that is all. Yeah. Okay. So, now I want to talk about something which is going to be useful for us as we go along, because there were a lot of questions on the first day, where does this thermal spectrum in the accelerated frame came, and I told you that vacuum has vacuum fluctuations, and these vacuum fluctuations are Lorentz invariant, but not generally covariant, and if you have an accelerating observer through the vacuum fluctuation, he will see it as a thermal spectrum. So, we need to understand what these vacuum fluctuations are all about, and that is what I want to explain next. So, I want to write down what is known as a ground state vacuum functional. So, let me try to explain that to you. Normally, we have, when we decompose this field into a bunch of oscillators, so each oscillator is labeled by qk, and remember that qk is actually a complex number. So, there is a xk and a yk, right. So, you have two oscillators for every value of k because it was complex. And the ground state of the oscillator is just exponential minus half omega times the square of the oscillator variable. So, if you forget this integration for a minute, exponential minus half omega k mod qk square is the ground state wave function for that particular oscillator. Now, I have a bunch of oscillators, and they are not talking to each other. All these oscillators are independent oscillators because we just added them together. Therefore, the ground state of the bunch of oscillators is the product of the ground states, and the product of the ground states of each of these qk oscillator here, which I have given with a big psi, and this is the set qk and 0. I mean, if it is so comforting, you can even think of it as q1, q2, q3, q4, q infinity. So, there is an infinite number of oscillators. That set is denoted here within curly brackets, and you take each one of the oscillators and write its ground state. Ignore the normalization, because normalizations in the end will take care of themselves, and most of the time it is infinite. So, you can only define relative quantities. So, that is proportional to exponential of the ground state of a one oscillator. Multiplication becomes the integration over d3k. So, this is the ground state of a particular field, because we kept putting this ket 0, which was the ground state of each of the oscillators, where all the oscillators are in the ground state, and what is it in terms of the field itself, and this is what it is. But it would be nice to write it in terms of the field rather than in terms of the Fourier quantity. That can be done. I will work with the massless case now. Massive case is a little more complicated. So there is just one trick which you need to know. This omega k for a massless case, when mass goes to 0, this is omega k is modulus of k. So you have a modulus of k times qk square and this integral. So you play a trick and you multiply by k and divide by k. So you get a k square on top and you get a k in the denominator. This half is this half. The reason you do this is that k square qk square, or rather ik qk, is the Fourier transform of the gradient. Qk is the Fourier transform of phi. Therefore, ik qk is the Fourier transform of gradient of phi. Hence, this quantity on the numerator is the Fourier transform of gradient of this, and this just gives you a 1 over 2k, which will just become a convolution. So you get the Fourier transform of 1 over 2k in the x space. So if it is too fast, let me just run it over once again. Think of phi, Fourier transformed into qk e to the ik dot x. Then gradient of phi is going to be ik times a qk e to the ik dot x. Then you get another ip times e to the I, again another gradient and a e to the I py. Then when you integrate over all k, that will give you a Dirac delta function, and k and p together will give you this. Now what is here is the Fourier transform of the remaining part. 1 by k Fourier transformed. Well, when you do a physics Fourier transform of 1 by k, you get 1 upon x minus y the whole square. Okay. Mathematically it is divergent, but we all know that 1 by r's Fourier transform is 1 by k square. Okay. So this is the result you have. So work it out, it is fairly straightforward. What it means is that I can write down this ground state wave functional actually as a functional of phi of x. So I am using the word functional a few times now, so let me just define it for you. A functional, I mean in John Wheeler's language, is a machine into which you feed in a function and it will pop out a number. Okay. So you take, this is a functional of phi of x. So you come and tell me some field configuration phi of x. You say that at a given time t, which I have taken to be 0, at that given time t, the field in space is like let us say 1 upon cos h square of mod x. Okay. So I know what that field is. So you go and plug in what is the probability for such a field configuration to exist in the vacuum. So you calculate that gradient and you do this integral, you will get a number. Of course, you do not know what that full number is because we do not know what n is. So if you give me two functions, one cos h square and one cos h to the power 4 or whatever, then I can compute it for both of them, and the relative probability for one field configuration to exist in vacuum compared to another field configuration to exist in the vacuum, I can decide based on this. Now this is exactly like in harmonic oscillator. So if I have a harmonic oscillator in the ground state, its wave function has a e to the minus half omega q square. So the probability that the oscillator is displaced by an amount q is given by e to the minus half omega q square dq. Forget dq, and this is the probability density which you get. And this is the amplitude for field not to be 0 but displaced by some amount. The reason people call it vacuum fluctuation is in some sense is historical, because people always thought that the vacuum should not have anything. But at the same time, if you take a ground state and of the harmonic oscillator and say that in the ground state of the harmonic oscillator, the displacement can be non-zero, nobody will bat an eyelid, because in quantum mechanics ground states are described by a wave function. So if you have a pendulum and or rather a pendulum oscillating, the minimum will be here, but the fact that it is going to be displaced by some amount q, you do get a non-zero probability amplitude for that in quantum mechanics. Just like that, classically the field is 0 in the vacuum state, but quantum field theoretically the field can have a particular value, and the amplitude for that field to have a particular value is given by this expression. Another beautiful thing to note, is that the theory is invariant under adding say 17.5 to the field phi. Otherwise, it would have been a bit strange. The field by itself does not come in, it is only the gradient of the field which comes in. So, the probabilities only depends on the gradients of the field, and there is an invariance under phi going to phi plus a constant. What you should take home from this, because the moment I start doing regular physics in accelerated frames and all that, these questions will pop up. Do not think of vacuum as mere emptiness. There is a non-zero probability for vacuum to host any field configuration you can write down. For some field configuration, this integral will diverge and go to infinity. Those field configurations have zero probability, but all other field configurations can exist in the vacuum. And the pattern of fluctuations of the vacuum is given by this. There is also one more thing which is very fashionable nowadays. It is called entanglement, which is already clear here. So, I want to connect it up with that because you will hear it somewhere. If I look at this quantity is the same as this quantity, except that I have used qk's as the variables here and phi as the variables here. So, this is a bunch of independent oscillators. These oscillators do not talk to each other. So, at one k and another k, there is no crosstalk between the two, and you can sort of check away half the oscillators and the other half oscillators would not care. But here the k is replaced by x. So, the field at a point x is your dynamical variable, just like this qk is a dynamical variable here. Field at a point x is your dynamical variable, field at one point x and field at another point x, they talk to each other. They are correlated and the correlation function just falls as 1 by r square. So, the gradient of phi here and gradient of phi here are talking to each other. So, now if you go and partition the space and say that I do not care what the field is doing on the other side, then there will be something non-trivial which will happen here, because across this surface with an 1 by r square correlation, the fields are talking to each other. So, the technical term is that the fields are entangled in real space, but they are not entangled in the Fourier space, because the Fourier space they are independent, but in real space they are entangled. And this leads to various interesting physics related to entanglement, etc., which we may mention sometime when we come to black holes, but right now I just want to point out that you can already see it from here. Okay. One important effect which arises because the vacuum is not mere emptiness is called Casimir effect, and this is probably the only exotic effect I will mention in this entire lecture which is experimentally accessible. So, this has been experimentally detected in different contexts. What that effect is, that it is a very beautiful example, and yet again, as I said, this is ripe for some project work and things like that, because there are lots of not completely resolved questions related to it. What it tells you is the following: you take two conducting plates, keep it in the vacuum. This is not your parallel plate capacitor. It is of course parallel plate, but it is not capacitor in the sense that you are not putting charges on it. So, there are no charges, no free charges, and you have two parallel plates kept in vacuum with a separation A. Then you will find that these two plates will attract each other. There is just two plates kept in the vacuum. They will attract each other with a force which falls as 1 by a to the power 4. Equivalently, you can say that the energy per unit area of the plate, because you are thinking of it as infinite planes. So, the energy per unit area of the plate is this quantity, the derivative of that is what is giving you the force. So, the energy is like this, and if A is smaller, the energy can be sort of lowered. So, it tends to come closer, it is an attractive force. The question is, why is it so? Now, there are different ways of doing it, and I will give you one particular method, and then I will tell you what are the caveats and why there is something curious going on here. So, the idea is that you think of vacuum and which has, let us say, modes. Okay. So, you think of vacuum filled with field modes which are running around in any way you like. So, think of it as electromagnetic modes, because the Casimir effect is measured for electromagnetic attraction between the two charged particles. This is an extraordinarily interesting electromagnetic phenomena in which E square does not appear. Okay. That is another mystery. You see, normally if you are talking about something electromagnetic, if the charge of some system goes to 0, then the effect should go to 0. And in fact, there is no free charges here, it is only h cross E, pi and A. Okay? But inherently it is electromagnetic. That is one of the mysteries, to understand it in a simple way, why E square does not appear. So, you have these modes which are going around. Now, you are going and putting two plates, but these are perfect conductors, so that the modes are supposed to satisfy zero boundary condition on that. So, these modes are no longer allowed, and only modes of this kind are allowed. So, the new vacuum state with the capacitor has modes which are not e to the ikx, but something like sin n pi by L or something like that in this direction. So, the new modes and the old modes are different, and if you go and work out your harmonic oscillator, the new harmonic oscillators and old harmonic oscillators are different, and then if you go and work out its energy, the new energy and the old energy are different. The difference between the two energies is what appears as the energy density between the Casimir plates. So, how do you work this out? Well, you can do it for electromagnetic field. Again, the standard reference for all of this I am going to quote is my book, and I have worked out in detail with proper regularization and all that, how to get that. But let me give you a quick and dirty way of thinking about it. So, take 1 plus 1 and you do a scalar field rather than electromagnetic field, where you have to be careful about boundary conditions and all that. So, you just assume that the field is vanishing at the two boundaries. So, without plates, you can say the wave vectors which are allowed, or this is one dimension. So, the k which is allowed are 2 pi by a times n, where n goes continuously. So, I had just for the sake of the dimensional reason, I have taken out a 2 pi by a, and this is n. K goes from 0 to infinity, let us say. So, this n goes from 0 to infinity. But if it is discretized, then it should be 2 pi by a times n, where n is integers. So, this is discrete and this is continuous. So, you can go and compute what is the energy difference. Essentially, it is half h cross times the omega. Omega is going to be 2 pi c by a, because that is what is going to kick in from k. It is as omega is just k. So, that is what I have written down here, 2 pi c has been reintroduced, times, in this particular case you are doing summation over n, and here you will be doing integral over n. This is the sum of all the integers, and this is the integral over all the integers, and both of them are infinite. So, the question is whether their difference is finite, and lo and behold, the difference happens to be finite. Okay. So, there is a respectable way of computing these things, and this is something which has Ramanujan's name associated with it, as to how to tackle divergent quantities and give it meaning. I mean, how can you add divergent quantities, multiply them, etc., and do it in a meaningful way. And when you do that, you will get this. But for your purpose, if you are curious, you do a simple thing. You change n to e to the, multiply it by e to the minus lambda n. Okay, then it becomes finite, because you have put a cutoff, and in the end of the calculation you take lambda going to 0, and you put a e to the minus lambda n here and integrate, and then you subtract it out and keep various orders of lambda, and you will find that all the divergent terms cancel out, and you will, it is the lowest order, you will get this result. So, this goes as a, because we are doing 1 plus 1 dimension, and we are working in scalar field. Electromagnetic case, if you do the corresponding calculation, you will get that 1 by a cubed, and the force as 1 by a to the power 4. So, this is, in some sense you can say that this is a beautiful manifestation of the ground state energy of the vacuum, right. If you take the ground state energy to be half h cross omega, which is what I have done here in both the cases, and you subtract the ground state energy of two kinds of oscillators, you get something. At least the difference in the ground state energy is something which you can see. So, you could ask the question, does this ground state energy gravitate? Does it produce a gravitational field? Okay. You do not need to know too much of GR for this, but let me just run through this, because I have not again seen this, I have not seen this explicitly spelled out. You can do a thought experiment to show that this ground state energy which you measure in the lab has to gravitate. So, what you do is the following, you take these two plates and you connect it to a pulley and put some weights here. This is sitting here, then you go miles away, and in that region you measure the gravitational field. Now, there is an Einstein's equation which tells you that the gravitational field, I mean this is some tensor which is built out of curvature and all that, has to be some constant times the energy momentum tensor of the source, and the source we are using is this, two masses and anything in between. We don't know whether something in between is going to be a source or not, but in principle it may be or it may not be. We want to find that out. The point is that when you do this with this TAB is equal to sum of these two, everything works out consistently. But if you just take this TAB, it won't work out consistently. The reason is the following. In the lab, once you have set this up and gone away, these two things will attract each other, they will move, that means the masses will move. Now, everybody knows that these masses are going to gravitate. That we are going to take for granted. Now, a moving mass will gravitate differently compared to mass which is standing still, because it has kinetic energy and all energies contribute to gravity. However, in Einstein's theory, this TAB should be something which satisfies a conservation law, because the left hand side satisfies that identity, so it has to be conserved. This TAB of the mass alone will not be conserved, because it is being acted by this force. How do I know it is acted by this force? Because somebody measured it in the lab. So, if I set up this thought experiment, I will find that it is going to go up and this will not be conserved, and you have to add this minimally in order to make it conserved. Now, I quietly reduce the mass slowly to 0 value. Then I conclude that this TAB of the vacuum has to still contribute to the gravity. So, this is beautiful, and many people believe that because of this maybe the 0 point energies are going to gravitate in cosmology, etc., etc. So, I want to caution you that I have not proved any of that. First of all, what I have proved is that the energy differences gravitate, because what is measured in Casimir thing is at best energy difference. Second, and that is the real what do you call the showstopper, is that it is possible to derive this effect, this Casimir effect I wrote down, without doing any of this. Okay? It is extraordinarily complicated, but it can be done. What you do is you take two metal plates and go and model the metal plates. There are two conducting plates which has electrons and lattice, and you compute what is the force between them. On the whole, it is charge neutral, but because of the fluctuation there is a force between them. You can compute it. And when you compute it, you will find that you are imposing finite conductivity. You find a force which actually depends on the conductivity of the material. But what is remarkable, what is not understood, what I believe is a good open project problem, is that when you take the conductivity going to infinity, it gives you this result. Not this, but the electromagnetic analog of this result. So, when conductivity goes to infinity, a term survives, and that gives you the force, and that term is independent of this E square. If you actually calculate it out in the electromagnetic way, it will depend on the charge of the particles, electrons, etc., etc. But in the infinite conductivity limit, you get a result which is very simple, which can be reproduced by saying that in the vacuum there are modes which satisfies a boundary condition. And when I say that the electromagnetic field is vanishing on the boundary, that is exactly what I am saying. I am saying that the conductivity is infinity. So, the infinity conductivity limit can be obtained from this, and if you do that, then this experiment is still true. It is still true that you have to put in this TAB of the vacuum, but it is no longer vacuum. It is the interaction energy of electrons in this plate with electrons in this plate. Of course, you have to put it in. If there is any kind of energy, that is going to contribute to the gravity, and that is just the interaction energy. Okay? So, what is really curious about Casimir effect is not so much as whether it will gravitate, it won't gravitate, etc., etc. How is it that such a complicated phenomena has such a simple explanation in terms of alternate explanation in terms of the modes in the vacuum and the boundary condition? Whenever something as simple as this happens and we do not have a reason, it means we have not understood it sufficiently deeply, and that is one of the things which is happening here. Okay. So, that is my last slide as far as this part is concerned. Now, I want to go into thermal effects in the horizon. So, I can probably spend another 10 minutes on that, or if you want to ask questions about this, and then we should do, what do you suggest? Yeah.
You mentioned about the normal equation is given that if you subtract the finite discretization from infinite, you will not get a finite.
Yeah.
In this actual case,
No, here I am subtracting one infinity from another. this is infinity, this is infinity. We are subtracting one infinity from another, and all regularization procedures involve subtracting one infinity from another and getting a finite number.
Computation, you said that the first one is a discrete number
Yes,
and second one is a continuous decimal.
that is correct.
Both are finitely countable. What's the meaning?
Not really, because integers is a subset of the real line. Yeah. Okay, that is what the difference comes out. Because if you take a real line, integers are only somewhere, no? There are in between places.
That comes out to be a very finite number, which is slightly surprising.
Yes, of course, it is not slightly surprising, it is remarkably surprising. And in fact, much of old string theory relied on it, because the summation of all integers happens to be minus 1 by 12. Okay? So, I would have thought that it should be at least decent enough to be an integer, positive, and it turns out to be negative. It is not an integer and it is a fraction. Okay? So, but it is true. I mean, because if string theories told you that, you need not believe it, but there are rigorous mathematicians who have said that there is a way of handling divergent series in which you can get this to be equal to minus 1 by 12. In fact, that computation will not even worry about this continuum. They will just say that this is the thing and you sum over all the integers, and we know sum of all the integers is minus 1 by 12, and that gives you the result. Okay? So, that is exactly how you get this 24 here, if you do it correctly. Okay? Fine. So, let me then go into the next one, which is in a different PDF file. So, I have to dig that up. Okay. So, this is what we have done so far is the background and preliminary, and this is the toolkit. So, most of the results in this we will be using in various places. That is why I collected together all these. And the first application of this is the temperature of a space-time, which I told you is one of the mysteries or a clues about putting together quantum theory and gravity. So, this I had I don't know whether I mentioned it, but in my opinion, this is the most beautiful result which you get in the interface between quantum theory and gravity. Okay? And what it says is that an observer who perceives a horizon will attribute a temperature to the space-time which is given by this. This was obtained by Paul Davies and Bill Unruh, and this is in fact in some sense much more general than the black hole temperature, because this applies to a much wider class of things and it puts it in a unified framework. For our purpose later on, just to give you a peep ahead, this allows you to associate a heat density with every event in space-time. Take this point at some given time. There exists an observer for whom there will be a horizon in such a way that this particular point will have a temperature, and because there is a horizon and some information is blocked, it will also have an entropy. So, there is a temperature times the entropy density, which is the heat density, which you can attribute to this. So, let me start with that and where it comes in the context. So, this is, you have a time and you have a space axis, and this is a space-like distance, and you take a space-like hypersurface and you take an event A. Now, in normal Newtonian physics, I can send a signal from here to here or here to here. There is no causal limitations in Newtonian theory, non-relativistic theory. But the moment relativity kicks in, it tells you that there is a horizon here for in this particular context, in the sense that this A cannot communicate to B because it is outside the light cone. There is some light surface which is going on here, and you cannot go from this A to B with a signal. You cannot communicate. Now, this is a very general and fundamental aspect of theory of relativity. This is why I said that if you are building a theory of quantum gravity, which many people do, without incorporating the fact that regions can become out of communication when you do general coordinate transformation, if you do not take that into account, and the fact that when that happens there is a temperature attributed to space-time, if you do not take that into account, you are just throwing away a deep clue about the nature of space. Okay, so, this is, where does this come from, or what does it implies to? So, if you take this particular horizon, Okay, let me also put in a word about horizon, because this will keep coming up. The simplest way to think about horizon is as a light front. So, imagine that I switch on a bulb here and light travels very slowly, then there will be a spherical wavefront of light which will be going from this point, right. So, it is just going outward, and after you have the light front going forward, you throw a stone. It will never cross the light front because the stone can never travel faster than light. So, material bodies can never cross a light front. Now, suppose the light front is going and you have some matter here which is gravitating, because of which it is trying to hold the light front back. That is, there is a gravitational force exerted on the light front. Either the light front will win or this will win, but there is a balancing situation where the light front is trying to move forward and the body or the gravitating force here is just holding it back and it stays put in one point. This is exactly what happens at the surface of a black hole. So, the surface of a black hole is not a two surface like you can wave your hand and draw in the real space. It is actually a light front, and the technical term for it is a null surface, okay, because null rays are what light rays are called. So, this is a null surface. So, this particular line I have drawn in 45 degrees is actually a null surface, because you can extend it. It is a planar surface rather than a spherical surface. So, it is a null surface and you cannot throw a stone from here in order to reach here. Now, what it implies is that I can have a family of observers here, let us say, which let us say asymptotes to this horizon. Then all of them cannot receive signals from this part of the horizon. So, they have what I would call a causal horizon. These observers are never, they are going to live here and they are never going to see anything from this direction. So, more precisely, you take the backward light cone from every event on that trajectory and you take the union of all the backward light cones and you take its limit, and that limit will define for you this causal horizon. When we go further with this, at some stage there will be this question as to, how can, are we talking about a physical situation, because we will be talking about accelerated observers, and no observer can be accelerated all the time. But it really does not matter. Of course, you have to add corrections because of that. It really does not matter because of the following point, which I want to get out of the way immediately. Suppose you have an observer who is doing something here, close to this, close to this, close to this. But after that, he is going to switch off his rocket motors and he is just going to stay put. What he experiences up to this point cannot depend on what he is going to do tomorrow. That will not be causal. Therefore, in some strict sense, if physics is at least quasi-local, then you should be able to obtain these effects even for realistic accelerations, even though in order to work everything out, we will assume that it is some kind of a uniformly accelerated observer all the time. Now, this structure exists in any space-time. Therefore, if this is going to have a feature like the temperature, that is also going to exist in all space-time. So, I want to just give you a taste of the space-times which will come up. At least two of them we will discuss very extensively, but I will mention three of them. One is what is known as the Schwarzschild space-time. This is the space-time of a simplest space-time of a black hole, and I have suppressed all the other dimensions and concentrating on just t and x. And the standard Schwarzschild metric in terms of the t Schwarzschild and r Schwarzschild is some 1 minus 2m by r, and this is dt square and this is dr square, with this coming in the denominator, which is what this minus 1 does. Now, you can immediately see that this can be rewritten in another coordinate system with some factor here times minus dt square dx square. How do you see that? Just pull out this quantity out, put a bracket here, then this will become 2, and then you redefine your dr square upon that quantity as a new time coordinate, and this is just the new time coordinate, it is just redefined. So, you can write it like this. So, the light cone structure in dt square minus dx square is the same as the light cone structure here, because ds square equal to 0 just kicks at this point. So, that is still 45-degree lines. So, that is what is drawn in this Tx diagram. What you will find that an r is equal to constant guy who is sitting outside the black hole will have a hyperbolic trajectory in that space time. This we will show later on, but just take it on faith right now. and he will see, because he is always going to stay outside the black hole, he will have a horizon and he is not going to get information from here. Now, here is another example. This is a de Sitter universe, which is the universe which seems to be asymptotically going towards. So, again it has the same structure. There is something here and 1 by that here. This is time square and this is the space square, and you can write it like that. So, again a person who is at a constant r will have this trajectory, and he will have a horizon at h inverse, which is on the outside. In the case of a black hole, this is a guy who is sitting outside the black hole and the black hole is out there, and it is the inside of the black hole which I cannot see. In the case of a de Sitter universe, you are sitting inside the universe, there is a Hubble sphere. From the outside you cannot get the information. Okay, so these are only that difference exists, but in the, as far as you draw the coordinate system, the fact that this is a hyperbola and it asymptotes to this line remains to be true. Now comes the simplest example, which we will spend lot of time, is actually flat space time. So, in flat space time, if you have an accelerated coordinate system, I will spend time and derive why an accelerated observer has a natural coordinate system and why it is given by that. Then the metric for that is exactly similar. There is something here and 1 by that comes here. So, that is the pattern I want to see in all of them. There is a factor sitting in front of dt square, reciprocal of that factor sitting here, and it can be mapped to flat space time with a conformal factor. The factor which is multiplying the whole thing is called conformal factor. In this particular case, that conformal factor happens to be 1, and you can actually map it back to this dt square minus dx square. So, this particular coordinate system you can invoke here, and you will again find that the observer who is sitting here quietly is an accelerated observer. He is hyperbolic in trajectory in the flat space time. So, it is this accelerated observer who is seeing a horizon here. So, these are the 3 examples we want to talk about, and again I want to give you a simple okay, it is getting, this we will do tomorrow. Okay. So, I want to explain to you why the horizons are hot, and the basic idea I had already mentioned to you, that in the normal quantum mechanics, evolution is given by e to the minus ith, and when you are talking about thermal physics, you work with e to the minus beta h. So, you see a correspondence between this beta and it. So, if some space time, when you analytically continue to imaginary time, shows periodicity and that period is given by beta, then the inverse of that period will give you the temperature. This is what is going to happen, that we will take up in the next lecture. So, this is a good time to stop. Questions? Yeah. Casimir effect, yes. With what? No, no. As far as I know, there are no corresponding experiments with insulators. No, it won't, because the point is that it is due to vacuum, but the vacuum requires a boundary condition that the field has to vanish on the 2 plates. If you put an insulator, field is not going to vanish. So, the vacuum will be the same with the insulator and without the insulator. Okay. Yeah. No. The time ordering, as I said, it is theta of T2 minus T1 and theta of T1 minus T2. This is completely Lorentz invariant and causal as long as the 2 events are time-like. When the 2 events are space-like, it will turn out that it does not matter which of these 2 you pick, because those 2 objects will be the same. Yeah. Yeah, okay. Yeah, if it is too advanced, I will tell you, we will discuss it. Yeah, tell me. Yeah. Yes, right. Right. Well, when you say C, it means that he has a detector. Now, he needed detector for a Dirac field, detector for a photon field, detector for a scalar field, etc. And each of those detectors will click, correct. they will register the same temperature. Now, except that fermionic detections are a bit tricky. So, if you are just talking about bosons, then it is easier. So, if you think that there is some hypothetical scalar field and there is a hypothetical, not hypothetical, just ordinary photon field, then if you have a detector for a photon field and a detector for a scalar field, they will register exactly the same temperature. Mathematically, you can show that it should also register the correct temperature for a fermionic detector, but it is very difficult to construct a fermionic detector. Yeah.
Suppose we have an accelerated manual state and one of the physics is goes inside the black hole.
Right.
Then and if we try to do some kind of measurement on the other, so like would this violate any type of?
Okay, this is still debated question, and it turns out that this is very closely related to this firewall paradox and information paradox and all that. So, there is no settled answer to it. Maybe we can discuss it if you drop by some time, but I do not want to get it into it in the class. Yeah. Yeah. Right. Yeah, that can happen. So, there are space times where these functions are different and they still have horizons, and as long as they have horizons and an observer perceives the horizon, he will attribute a temperature to it. These three I took because these are the simplest kind of cases where you can work out things very easily. Yeah. Yeah.
Or if say the coordinates are like ESDT or mixed
Oh, that doesn't make any difference, because all these cases, if okay, in two. Okay. Firstly, in 2 dimension there is a theorem which says it can always be written as a conformal factor multiplying minus dt square plus dx square. Okay. This is actually quite easy to see, because in 2 dimension there are only 3 independent variables, a, b and a into dt square, b into dx square and a c into dt dx. Now, there are 2 coordinate transformations which are allowed for you, because there are 2 coordinates. So, you can mix them up in any way you like. So, 2 function degrees of freedom are available out of 3 functions. So, you can arrange in such a way that there is only 1 degree of freedom left, and it is convenient to take it as omega square into minus dt square plus dx square. Therefore, in 2 dimension life is very simple, and we will be spending lot of time in 2 dimension because of this reason, and you always have something multiplying minus dt square plus dx square. Now, if you go to 4 dimensions or and work with that, most of the time it turns out that all the important physics which we are talking about is in the 2 dimensional sector. Like for example, if you take Schwarzschild metric, the theta and phi directions really do not contribute anything non-trivial. Of course, if the black hole is radiating, that radiation will backscatter from the curvature, and there is something called a transmission coefficient through that curvature. There are extra complications which come about like that, but essentially the kind of physics which we are talking about, this temperature, entropy, etc., they do not depend on that. So, in all dimensions the same kind of an idea will go, and there are cases where there is something called a finely coordinate system, in which you do have a cross term, TTDR kind of cross term, but it still works out. You can do that even in Vidyametric, yes, but it becomes much more complicated than these metrics. In principle, you can do that. Vidyametric in 2 dimension it is easy to do, but if you do Vidyametric in 3 dimension, it is very non-trivial. People have tried to use that to model an evaporating black hole with the radiation going out be sort of contributing to the Vidyametric, and that is technically much more complicated. Yeah. Right. How do you do that? Because if you, a spinor really does not have some kind of a sensible non-relativistic limit. I mean, you can write down non-relativistic spinors and work with them, but as far as the limit is concerned, you will get essentially the same thing. In the relativistic case, for some peculiar reason, because the Dirac, you know that the Dirac-Lagrangian is linear in derivative, right? While the Klein-Gordon-Lagrangian, for example, has a quadratic term. Because of that, when you actually work this out, you will find that in the case of a Dirac field, the propagator essentially moves along 45-degree lines. That is, you take one point and take another point and take all paths where every little bit is a 45-degree line. And it is actually completely trivial result which you can derive once you know the Dirac propagator. This is done in my book as an exercise. That is, given the Dirac propagator, once you know Dirac propagator from the standard theory, how to write down a path integral for this. And this is, interestingly, this was worked out in complete, it is mentioned in Feynman and Hibb's book, but he sort of makes it like a mysterious thing. But it was demystified in one of the papers by Jayan Narlikar. In one of the early papers by Jayan Narlikar, he actually works this out. But that doesn't get you spin. That is what I was trying to say. Yeah.
I have two questions. One was that finally you derived that after all these things, our system turns out to be a system of harmonic oscillators.
That's correct.
So, and since you extensively used the Fourier transformation method,
Right.
so is it true that maybe since the result that we came up with the system of harmonic oscillator has to do with the Fourier fact that we use Fourier transformations, which is just a superposition of sine, cosine?
No, because Fourier transform has nothing to do with oscillators by itself.
No,
Of course, there is a e to the I k dot x.
Yeah. So
Okay, that is, no, that is not the reason at all. It is much more deep, much deeper than that.
Okay. And second question is that when you will calculate the energy, total energy of a single of a loop
Right.
at a point, it turns out to be infinity, and there is no information of space.
Correct.
Time.
That's right.
So, since the fact that it turns out to be infinite, and it doesn't have the information of time and space, any trajectory. So, does it mean that we have unintentionally integrated over all those information and get an infinity?
No, the infinity is because we integrate it over something. If you look at the density, it is finite, right? But that doesn't tell you anything, because the density by itself is not something which is observable or related to anything else. So you can, if you want finite quantity, just take the integral out, and you say that every oscillator has a ground state energy which is half h cross omega. That is a finite quantity. But what does it buy you? Because there are infinite number of oscillators and you have to integrate it. But if you are doing condensed matter physics, for example, then you have phonons, and the phonons are lattice vibrations, and each of these vibrations is like a harmonic oscillator, and it has an energy half h cross omega. But the number of oscillators there will be finite, because there is a lattice spacing which puts the high energy cutoff, and the size of the crystal or whatever you have puts a low energy cutoff. So there is a nice cutoff at both these things. So here the point is that in physics, when you are doing this field theory, if you assume space-time is continuous and there is no 0 point length to the space-time, then this integral you have to do some kind of a manipulation to get finite answer out of it. It won't come out naturally. Yeah. Right. Correct. Right. You can actually do, this is massless scalar field which I did. Okay. You can do it for a massive case as well, and you get answer. But the Green's function won't be 1 upon x minus y the whole square. It will be a Macdonald function. So it's much more complicated. Okay. Essentially, it is the static part of the propagator which comes in. So the propagator for a massless case is 1 upon x square, and when t minus t prime is equal to 0, while the propagator for a massive particle is a Macdonald function. So it will be more complicated, but you can work out the whole thing. Yes. Yes. No, the scalar field Casimir effect is a fraud. There is no scalar field Casimir effect because we don't know any material on which the scalar field has to go to 0. So, think of the electromagnetic Casimir effect, which is the one which has been observed in the laboratory. In that you have a conducting plate and the electric fields vanish on the conducting plate, and that happens because there are charges milling around and the charges are coupled to the electric field, and that coupling is governed by E square, but the final answer is independent of E square. That is why it is surprising. Yeah. That is correct. Because the thought experiment which I have used said that take the two plates in the laboratory, connect to a pulley, this, and then when it moves, that energy which is causing the motion, which is providing the kinetic, because what is making these two masses go up? That is the energy which is reduced between the plates when they come together. That energy is given to the kinetic energy of the bodies. Now, the energy which is reduced when the plates are coming together is the energy difference between with plates and without plates. So, we do not know without plates if I have just vacuum energy whether it is going to gravitate or not. At least this argument does not say anything about it. Yeah. Let me take that first. Yeah. Yes, yes. So, if you have a medium, then there is a different pattern of fluctuations, yes. Yes. No, in fact, that was the alternate derivation I told you. If you take just two conducting plates and you take the fluctuations of the fields in this plate and the randomness of the electromagnetic forces there, etc., you get a fluctuating force which you can compute, and that force on the average turns out to be equal to the Casimir force. So, that is the nitty-gritty computation using two conducting plates, and the important thing is it depends on the conductivity, and you can write down the expression. This is there in textbooks. Exactly, exactly. And then when that sigma goes to infinity, something falls out. That is the part which we do not understand. And there are other curious things about it. For example, we took two plates. Suppose I make a cube, okay? Then you put boundary conditions on all directions. You calculate the energy with the box and without the box. Then you get something. Then you sort of slowly distort this cube into a sphere, okay? Then it turns out that the sign of the energy changes. So, you can't even guess a priori whether the energy difference is going to be negative or positive, whether the Casimir forces are going to be attractive or disruptive, okay? I mean, in the original literature, when Casimir found this, he thought that there is a way to find the shape of the electron, because if for a cube it is one sign and for a sphere it is another sign, he thought that there must be some shape in between where it is strictly 0, and that could be the shape of the electron, etc. It never worked out that way. So, there are things which are very counterintuitive about the Casimir effect. Yeah. Okay. Do the calculation for what? But you need some metal plates. Right. Exactly, exactly. Okay, let us take it tomorrow.